In this lecture, we can see the allowable axial stress, how we can calculate it. Allowable axial stress, axial compressive stress FA, that represents the maximum compressive stress a member can withstand without experiencing buckling. This just depends on the geometry of the member. Like geometry means diameter to thickness, that ratio based on that geometry of the member, as well as its material properties like Young's modulus and yield strength of that tubular. Depends on these material properties as well as geometric considerations, geometry of the member, the allowable buckling stress we can, allowable compressive stress we can calculate it, and its susceptibility to buckling, that also one important factor. So for members with a slenderness ratio such as d by t less than or equal to 60, the axial stress is determined using one of the two equations depending on whether the member is slender or not. So if it is less than or equal to 60, we can see we have two equations. Depending on that, we can see whether the allowable stress for non-slender member as well as allowable stress for the slender member. We can see we have two formulas here. You can see this is for the allowable stress for slender member. It depends on whether the KL by R ratio is greater than or equal to CC or less than or equal to CC. If it is greater than or equal to CC, we are going for slender member case, where this this equation primarily reflects on the material's elastic properties. You can see Young's modulus and then KL by R squared. There is this value does not depend upon the yield value. If this member is slender, it does not depend on the yield value for the allowable axial compressive stress. This equation primarily reflects the material's elastic properties and provides the upper bound for the allowable stress whether the member is very slender and prone to buckling. When the member is very slender and prone to buckling, if these things are depending on the d by t ratio less than 60. If it's more than 60, then we need to consider another factor like local buckling also, that we can see it. So here if you see this equation for non-slender members, equation for axial compressive stress, FA equal to 1 minus KL by R squared by 2 CC squared Fy. Here part this is function of Fy, and here denominator also it is that depends on the KL by R ratio. K is the effective length factor, L is the unbraced length, and R is the radius of gyration, Fy is the yield strength of material. Here you can see CC is the critical constant that is defined in the using the parameters of E and the Fy. It's a square root of 2 pi squared E by Fy is the Young's modulus, and then CC that represents the material's resistance to local buckling under axial compression. So what does it mean, CC? CC actually represents the material's resistance to local buckling under axial compression. This equation accounts for the member's material properties as well as its slenderness. As the member becomes longer and more slender with higher KL by R, the likelihood of buckling increases, so that allowable axial stress decreases. So if the KL by R ratio, this is the KL by R ratio, we will call slenderness ratio. If slenderness ratio is high, this is the slenderness ratio. If keeps on increasing, then this is our FA. It will keep reducing. If slenderness ratio increases, allowable stress it will come down. Next we can see it. Let us see about the other formula, that is for the slender cases, that we have seen it right just before. Here you can see, based on the slenderness, if the KL by R ratio is greater than CC, it becomes a slender category. Then we can calculate the FA value based on 12 pi square E by KL by R square. Does not depend on the yield value. Another thing is that local buckling considerations. When we have the local buckling, that means d by t ratio is greater than 60, local buckling becomes a significant concern. So when the d by t ratio becomes more than 60, local buckling becomes a significant concern, and local buckling occurs on cylinder's wall when the cylinder's wall buckles under compression before the entire member fails due to global buckling. Instead of the, for example, this is the member. Instead of this member buckling as a global member, if you see the tubular walls, this tubular walls, it can locally buckle because of the diameter is too large and the wall thickness is too thin. Then it has more susceptibility for this kind of local buckling. So before the entire member fails due to global buckling, the cylinders will buckle under compressive stress. Locally it will buckle. This is especially important for a thin walled cylindrical members. You can see this is really important for the thin walled cylinders. If wall is very thin, then it is high chance that it can easily buckle locally. The elastic local buckling stress, another one is inelastic local buckling stress. There are two things, FXE, that's elastic local buckling stress. Another one is FXC, that is inelastic local buckling stress. Fx is the stress at which member will start to buckle elastically without permanent deformation. It's known as elastic local buckling. So it means like without plastic deformation, without permanent deformation, the member will locally buckle elastically. So if you take out the load, this buckling it will go back like this will behave like a elastic local buckling. Before the column fails, the member it will locally the wall thickness it will locally buckle under elastic condition. So if you take out the load, it will go back to its original position. That's without permanent deformation it's happening. So that's the thing, like FXE it calculates, that's the stress at which the member will start to buckle elastically. Here FXE equal to depends on 2CE and then thickness by diameter. Here C is the critical elastic buckling coefficient. That's nothing but critical elastic buckling coefficient. CC is nothing but the coefficient C. It is theoretical value is 0.6, but a reduced value of 0.3 is recommended to account for geometric imperfections. Thus, to account for the geometric imperfections, the C value is reduced. And E is the modulus of elasticity, T is the wall thickness, D is the outside diameter of the cylinder. The formula estimates the stress at which level cylindrical wall will elastically buckle under axial compression. This is the thing it's explained here. Then if you go to the next thing is the inelastic local buckling stress. Here we can see inelastic local buckling stress. When the compressive stress exceeds the elastic range and the material may deform plastically before buckling. So material deforms here plastically before the entire column buckles, before the global buckling happens. Locally the material will become plastic permanent deformation locally. Plastically it will buckle. This inelastic local buckling stress is given by 1.64.23 d by t square root of 0.25 like that. Power 0.25. Fo is the Hilson, d by d is the thickness to diameter thickness ratio. This equation provides a stress at which member undergoes inelastic deformation. That means permanent deformation before buckling. Before buckling happens, this undergoes inelastic deformation. So this is very clear. The material undergoes inelastic deformation before buckling. It also ensures the stress level stays below the elastic buckling stress. So it happens it's below the elastic buckling stress. It will come. The critical local buckling stress, in cases where dB exceeds 60, local buckling stress becomes a limiting factor. To account for the critical local buckling stress, either Fe or Fc should be used in place of Fy when calculating the allowable stress. This ensures the design prevents local buckling by taking into account both elastic and inelastic buckling. So we can avoid the local buckling by taking into account the elastic and inelastic buckling behaviors. For members with dB less than or equal to 60, local buckling does not significantly affect their axial stress calculation, thus the stress is simply equal to Fy factor. So overall buckling behavior for members with slenderness ratio KL by R less than CC, allowable axial stress computed equation 6.2, which accounts for both material and geometric vectors. If it is a slender member, when KL by ratio is greater than CC, different equation used. For members with high dB ratio, that's a potential for local buckling is considered by calculating elastic and inelastic buckling stresses. The smallest of these stresses are used as the critical stress in place of FO in buckling analysis. These equations ensure design structural takes to account both global and local buckling behaviors. That's how we can see this. This is the VBA code. You can create it. VBA code. Here if you see it. First thing we need to calculate the dB ratio and check if the dB ratio is greater than 60. If it is greater than 60, local buckling is a concern. Calculate the buckling stress like elastic local buckling stress and inelastic local buckling stress. This is to account for 0.3, used to account for geometric imperfections. Inelastic local buckling, so output we can see these two we can limit, and if no local buckling concern, these two values are not okay, and we need to calculate the CC value also. Based on the CC value and scale by ratio, we can use which equation to whether to non-slender members or slender members. Like that we can use it. The next one numerical example, we can see it here. The modulus of elasticity, Young's modulus, and Fy value, and brace length, radius of variation, K factor, diameter, thickness. So dBT is 650, it's less than 60, so we no need to consider local buckling, but it will be checked for completeness. So we need to determine the allowable axial compressive. So first step is to calculate CC. So first step, immediately you need to calculate CC. That is nothing but square root of 2 pi squared E by Fy. That's this formula, right? So once you plug in the values, you can get 70.6 meter. Then calculate the KLBR ratio. KLBR ratio comes as 50 in this case. Then if you compare KLBR ratio to CC, then it's less than CC value, so it becomes a non-slender member. So non-slender member case, we know the formula for non-slender member case. Once we plug in all these values, we can get this FA value that becomes 67.6. The allowable axial compressive stress is 67.6. Local buckling is not applicable, right? So since dBT is less than 60, local buckling is not a concern. No further checks are required for local buckling. Therefore, member can safely carry an axial compressive load of 67.6. You can see it here. Here you can see the equation 6.2, non-slender member, then slender member, then critical constant CC, then buckling, elastic buckling stress. We can see the FA value used for calculating the allowable axial compressive stress. FA for members where the KLBR slenderness ratio is less than CC value helps ensure that the member does not experience buckling under uniaxial compression according for material and geometric parameter factors. And the next one, if you see it, this one is FA value. This for slender members used for calculating the axial stress for very slender members. KLBR ratio is greater than CC. This equation simplifies the calculation based on the material's elasticity. This provides more simplified calculation for slender members, focusing on the material's elastic properties rather than the complex geometric interactions. And CC is nothing but the critical constant CC. That will limit. That defines the limit where the member changes from non-slender to slender. It's a function of material properties. It's just a function of E by Fy. It's a function of purely E by Young's modulus and yield strength, purely the material properties function. That's a critical constant. That defines whether the member becomes slender or not slender. This determines whether a member behaves as a non-slender or slender elements and helps in choosing the correct equation for buckling analysis. So you can see CC is nothing but purely whether the member becomes slender or non-slender. It's a function of E by Fy. It's not only function of whether the member is slender or non-slender. Not only the function of geometric parameters, but also the material properties. So this becomes like a global buckling case, like whether the member becomes slender or not slender, like that. For the elastic local buckling stress, this depends on the material properties as well as geometric parameters. But in case of CC, it does not depend on geometric parameters. Okay, calculate the elastic buckling stress for thin-walled cylindrical member. So this local buckling, it always happens for thin-walled cylindrical member only. CC is the elastic buckling coefficient and depends on the material property and geometric properties. Provides a stress at which the cylindrical wall will elastically buckle under compression, assuming no permanent deformation occurs. Usually no permanent deformation occurs for the elastic local buckling. Before that, how much is going to affect. Next one is that Fy. Calculates inelastic buckling, local buckling stress for a cylindrical member when the stress exceeds the elastic range, allowing for plastic deformation. Ensure that members subject to higher stresses are analyzed for the inelastic behavior buckling. Elastic behavior buckling, especially when the member deforms plastically before buckling. The next one is critical local buckling stress, Fxc. Equal to Fy. If it is less than 60, it becomes automatically equal to Fy. If the diameter thickness ratio is less than 60, no local buckling is expected. If it's more than 60, then critical buckling stress must be used, Fxc. used when deviated ratio is greater than 60 to calculate stress at which local buckling becomes a limiting factor. If deviated, let's say no buckling correction is required. Slenderness ratio KLPR. So this is a ratio of unbraced length to radius of gyration. K is the effective length factor depending on the column's end conditions. That depends on the column's end conditions. Important for defining the susceptibility of the member buckling. Member to buckling. A high slenderness ratio means member is more prone to buckling. High slenderness ratio means member is more prone to buckling. Let's have some group discussion with people. Let's have a group discussion. Hey Alex, I think I'm ready to calculate the axial compressive stress for this new column design, but I can't quite figure out how to check the local buckling. It's also complicated. Hi Jamie, welcome to the world of steel design. It's like solving a puzzle with formulas. Do you worry? Don't worry, you got this. Let's start by checking the dB ratio. That's the first thing we need to figure out. What's the first thing we need to figure out? Calculating the dB ratio. Let's start by checking the dB ratio. That's the first thing we need to figure out. dB ratio, what's that, and what's the whole local buckling thing? Let's break it down. The dB ratio is simply the diameter of the column divided by the thickness of its wall. If the ratio is too high, say over 60, we need to check for local buckling. It's a nasty problem where the column walls could buckle under compression. dB ratio is above 60, we need to calculate two things. One is elastic local buckling stress, another one is inelastic local buckling. If not, we can focus on axial allowable compressive stress only, which is the force column can handle without collapsing. What's that? That's the force column can handle without collapsing. But don't worry, I have got the magic formula right here in the Excel file, ready to see the power of EBA. Magic formula in Excel. What are we waiting for? Show me. Alright, here's the deal. First we need to input the basic information of the column. First what we have to do, we have to input the basic information of the column like modulus of velocity, unbraced length, radius of gyration, diameter. I will let you put in these values, you got this. And enter the following modulus of elasticity in the particular cells and got it. Let's see modulus of velocity are these values. Now before we calculate the axial stress, we need to check for the local buckling. If the dB ratio is greater than the 60, we are going to get some kind of serious calculations for buckling stress. We don't want this column to buckling under pressure, right? And boom, here's a magic Excel VBA code will check everything for you. Oh, it's just calculate everything. The allowable axial compressor is displayed, and because the dB ratio is 50, it's not even a local buckling problem. It's not applicable for elastic and elastic bucklings. How does it all know this? This is the power of good design and smart programming. The VBA code checks for conditions, automatically calculates stress and tells you what's what. Even if it's not applicable, if you don't worry about the local buckling, it's like having super power assistant. That's right. Let's have one more group discussion with engineers. Hey Alex, I have a question. What's the difference between axial compressive stress and local buckling? These are two different things. Let me explain. First, let's talk about the axial compressive stress. It's the force the column can safely handle when it's compressed all along its length. For example, think of a steel column standing tall in a building. We want to know the maximum force it can carry without failing. Okay, I get that, but how do we calculate it? We use formula. But first we check the column. First thing we check is that. But first we check if the column is at the risk of local buckling or not. So if the column's diameter is too big and wall thickness is too thin, the column might buckle locally. That means wall could fail before the whole column. That's called local buckling. We call this local buckling. Oh, if the column is too thin, it could collapse or bend in sections instead of just carrying the load, right? Yes, exactly. And that's where the dB ratio comes in. If the dB ratio is too high, we need to calculate the stress at which the wall will buckle. If the dB ratio is greater than 60, we need to use two formulas. For elastic buckling stress or one for inelastic local buckling. So here's the one for elastic local buckling. 2CE T by D. C is the coefficient, E is Young's modulus, T is thickness, D is the diameter. That's okay. When the column is compressed, the wall could bend elastically, but it has not reached its limit yet. It could buckle elastically, but it could bend elastically, but it has not yet reached its full capacity, right? For inelastic buckling, we use different formula. This one tells us how much stress the column can handle before it becomes permanently it buckles in a more permanent way. This tells us how much the stress column can handle before it buckles in a more permanent way. Testing of column. Now here's the most important part is that we compare the stress we calculate with the yield stress of the material. If the column stress is too high, it might buckle before it can hold the load. This is where we get the critical local buckling stress, CC, critical local buckling stress. That we use the modulus velocity exponents to find out the value called CC. If the column stress is below this value, then we know it's safe from local buckling, no need to worry about it. Otherwise, we need to worry about it. Let's see the other factor also. Okay, if we have the debate ratio is less than 60, we don't need to worry about the local buckling. We can calculate the allowable axial compressive stress directly with this formula. If the ratio is more than 60, we have to worry about the local buckling, and we need to check for local buckling first using the formulas, also other formulas. If everything checks out, we can confidently use the allowable axial compressive stress in our design. But if local buckling is a problem, we need to adjust the design to make sure the column won't fail. I think I finally understand. We calculate the stress, check for local buckling, use the formulas, keep everything safe. That's right. Now you know how to do it all in Excel. With the right tools, engineering can be a lot easier. I'm ready to design some columns.